Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 17, seminar 8, in which we will solve our next problem, number 18, or the problem known as the Chain of Pappus, named so after the ancient Greek mathematician Pappus of Alexandria, who lived roughly or approximately between the years of 290 and 350 of Common Era. This problem is absolutely amazing because it brings front and center the tactical power of the transform and conquer problem solving approach. And in order to comprehend that statement, let us understand what is required of us in the chain of Pappus problem. In this particular problem, we're given two generating circles. The outer generating circle Q1 shown on the left side of your screen in olive green, and the inner generating circle or a smaller generating circle Q2 shown in olive green over here. And these two generating circles are positioned with respect to each other in such a way that the smaller circle touches the larger circle internally at a point to which we will refer as T for tangency. And it is given to us that the radius of the circle Q1, designated with the uppercase letter R1, is strictly larger than the radius of the second circle, designated with the uppercase R2. These are two real numbers, and this is the relationship between them. We will need this relationship very, very soon. Due to the mutual juxtaposition of the generating circles Q1 and Q2, they trap between them a certain planar region, and into that planar region they're inscribed a family of, let's say, blue circles shown over here, and this family of inscribed circles is generated as follows. Let us say that the straight line of centers, which in the book I named as lowercase l, or the straight line that passes through the centers of the generating circles Q1 and Q2, shown in blue over here, intersects our generating circles at the point B0 over here. That is the point where the straight line of centers intersects the smaller generating circle, in addition to the point T where both circles meet. And the point A0 shown over here is the point where the straight line of centers intersects for the second time the outer generating circle Q1. Consequently, as the first step, we use the line segment A0, B0 as the diameter of the first circle of the inscribed family of circles. This circle is shown over here. I named this circle as K0, and in general, that family of circles is after that generated as follows. Even though constructing the first circle of the inscribed family of circles is straightforward, as I explained, right now inscribing the consequent circles in the planar region trapped between the generating circles, the outer circle Q1 and the inner circle Q2, is not really that straightforward, but that is besides the point. These circles are inscribed as follows. Each consequent circle touches the first inscribed circle, K0, externally, and then it touches the smaller generating circle, the green generating circle Q2, also externally, but it touches the larger or outer generating circle internally. And then it touches every next neighbor of that circle also externally. So we have, in general, we have 4 points of tangency. The point here, 2 here, 3 here, and 4 over here. And every consequent inscribed circle gradually gets smaller and smaller in size, but it touches the generating circles as shown over here, and it also touches its immediate prior and immediate consequent neighbor as shown over here. Consequently, The objective or the challenge in the chain of Pappus problem is the following. Let us say with the lowercase r and the subscript n, we will designate the radius of the nth inscribed circle. And due to the symmetry of the arrangement, it is evident that our family of inscribed circles will grow to the right of, let's say logically to the right of the line of centers and to the left. I do not show it on the board, but in the upcoming professionally made diagram you will see that. So the numbering of the circles from the inscribed family will go symmetrically. The very first circle, as I explained, which we construct as I explained a few seconds ago, we number with 0, and then the next circle will be 1, 2, 3, and so on. And likewise, this numbering will go to the left of the line of centers. And the objective of the problem is to find the expression for the radius of the nth inscribed circle as a certain function of the length of the radii of the generating circles, uppercase R, 1, 2, and the ordinal number of that circle n. Now we know that Pappus of Alexandria lived several hundred years after another ancient Greek mathematician known as Apollonius of Perga. And Pappus of Alexandria actually wrote certain amount of works about the works of Apollonius of Perga, and we now know that Apollonius of Perga put together the definition of the inversion of the plane with respect to a circle, with respect to a hyperbola, and with respect to a parabola. So even though this is not a statement of fact, this is an assumption, but it is a plausible assumption that Pappus of Alexandria, since he wrote about the works of Apollonius of Perga, who introduced all these wonderful types of inversion, also was aware of inversion of the real plane, at least with respect to a circle. However, we also know that we have documental evidence that Pappus of Alexandria solved this particular problem without using inversion of the real plane with respect to a circle. His proof apparently ran for several pages. It was quite lengthy. It used nothing but the machinery of what we now refer to as elementary plain Euclidean geometry. It was apparently not that easy on the eye, but with the help of the transformation that we're studying in this course, the inversion of the real plane with respect to a circle, the solution of this problem becomes a child's play, and pretty much any sufficiently motivated middle school student these days who is aware of the Pythagorean theorem and the workhorse formula that defines the inversion of the real plane with respect to a circle will be able to solve that problem. And now, since the cat is out of the bag, what we do over here is the following. In order to solve the problem number 18, also known as the chain of Pappus, we perform the following maneuver. We pick the point T to be the center of inversion, and we pick the distance from the point T to the point A0, or twice the radius of the outer generating circle, twice R1, as the radius of inversion. And consequently, the circle of inversion will be the circle that is centered at the point T and has the distance A0T as its radius. I do not show the circle of inversion. We do not really need it right now. This problem is actually quite real estate hungry, so I want to save as much space as possible. But under that inversion of the parent plane, with respect to the circle thus defined with positive power ones, what do we observe? The straight line of centers, L, that runs through the center of inversion will be taken into itself. We already know that much. And precisely because the generating circles, the outer generating circle Q1 and the inner generating circle Q2, are orthogonal to the straight line of centers, we know that under inversion, of the real plane with any power, the magnitude of the angles and the tangency points are conserved. That means that the images of these 2 points under the chosen inversion will remain orthogonal to the straight line of centers, and according to the theorems that we proved early in this course, both of these circles will be taken into these straight lines. The outer circle Q1 will be taken into the straight line shown over here, and the inner generating circle Q2 will be taken into this straight line shown over here, because the point B0 will be thrown outside into this point right here, B prime 0, and these 2 straight lines will be perpendicular to one and the same straight line. That means that these straight lines will be parallel, and one of the characteristic features of parallel straight lines is what? Is the fact that the distance between these 2 straight lines will be one and the same at any point, whichever we decide to measure that distance at. And that means that this amazingly complicated family of inscribed circles, where the radii of all these circles vary in some interesting way, which we're about to discover, in their reflected or inverted version, they all become the same. The radius of all these circles becomes one and the same, and the radius will be equal to half the distance between these 2 parallel straight lines. Now, I did this drawing that you see on the left side of your screen by hand and by eye. This is mostly a schematic, but when that diagram or that construction is carried out with professional tools, I use the free software called GeoGebra. You are more than welcome to use any other graphic package, and you actually should carry it out. And when you do that, you will see that this particular construction will look as follows. In my problem-solving career, I discovered that one of the best ways to check if your geometric construction was done correctly or not is to animate that construction in some way and wiggle several key or strategic or characteristic points in your construction and see if your construction is coming to life in the correct way, that all the objects of interest are manipulated in a way that actually makes sense. And in addition, creating an animation of this or that mathematical idea or mathematical phenomenon is also fun in its own part. So here, for the benefits of everyone else, I have created an animation of this particular situation where the chain of Pappus is inverted into a problem that is basically trivial to solve. I created this animation using the free software called GeoGebra, and in the animation that you're about to see, I fixed the outer generating circle shown in olive green, and the only thing that I did vary in the upcoming animation that you will see is the position of the point B0, basically the diameter, if you will, or the radius of the inner generating circle will breathe a little bit up and down over here. It will dance along the straight line of centers L. I did not designate it again to save space, but this is what you will see in the upcoming animation, that the point B0 will dance a little bit up and down. The size of the circles from the inscribed family shown in blue will vary in some way, but you will see that under the appropriate inversion that I just explained in the previous segment, these straight lines, which are the images of the outer and of the inner generating circles, will remain parallel, and all the inverted circles will also have one and the same radius for a chosen position or for a fixed position of the point B0. But as this point moves, the size of the family of these circles will change, but within each particular instance of that change, the sizes of the circles will remain one and the same nonetheless. In mathematics, this problem will be qualified as a problem to find, since in this problem we don't really have to prove anything, and consequently, before we deep dive into the underlying computations, I suggest that in a separate tab in your browser, you pop open the free PDF file or a chapter from my free book called Inversive Geometry for All, on which this seminar is based, and follow along the printed material, if you will. It is also a good idea for you to construct the setup of the input objects for this problem using your favorite graphing software on your own. Before we proceed, as I explained, the key over here is to pick the inversion of the real plane with respect to the circle C. I do not show it in the diagram, but in the professionally made construction that you saw a few seconds ago, I do show it. This is the circle of inversion. It has the center at the point T where the generating circles touch each other, and the radius of this particular inversion that solves this problem in the trivial way is twice the radius of the larger generating circle. It is also a good idea for you to grab a piece of paper, grab a pen, and follow along. Number the upcoming equations or relations that we will develop so that you can refer to them in your own paperwork in an easy way. And it is a good idea for you to trail my numbering, because I will refer to the numbered relations because I simply do not have enough room in the board. To that end, we have a low-hanging fruit that we can pick right away. And what is that fruit? Remember that once we pick a fruitful inversion that solves this problem, trivially, we have a family of circles that all have one and the same radius for a fixed input, radii of the generating circles. And the numbering of these circles will obviously be the same. This family of circles we can refer as K0, circle K1, circle K2, and so on, circle Kn. The inverted family will be referred with the prime or with the prime notation. For example, B prime O is the image of the point B0 under the chosen inversion, and in the corresponding theorems we actually proved how to construct these straight lines, and the byproduct of that construction is precisely the image of the point B0 under the chosen inversion, which is the point B prime 0. The point A0 shown over here will remain fixed or stationary. The power of inversion is positive. Remember by the corresponding theorem that every point that sits on the circle of inversion remains where it was when the power of inversion is positive, which is the case. And for that matter, let us write down that the power of inversion is positive. The power of inversion is positive power. And once we cut the distance between the images of the input generating circles in half with this straight line shown right here, then the center of the first inverted circle we will designate with uppercase O prime 0. Then the center of the second inverted circle will be O prime 1, and so on. The center of the nth inverted circle will be O prime n, and so on. And one observation we can make right away is that the distance from the point O prime 0, this point right here that lives on the straight line of centers of the generating circles, to the center of the nth circle, O prime n, that distance we will designate as D prime n. We can make a trivial observation because that distance goes in pairs, one radius and another radius. You see, that's the diameter actually of all these circles. Another radius and another radius, another diameter, and so on. And that means that we have the following relationship between the distance of the center of the nth inverted circle to the line of centers D prime n is counted in twice the radius r prime of the nth inverted circle, and we multiply this by the ordinal position of that number. The 0 circle, the distance is 0. The first circle is twice the radius of the inverted circle, and so on. And also don't forget that precisely because the radii of all the inverted circles is one and the same, it doesn't really make any difference, or doesn't really bring any new information to designate this radii with the nth, with the subscript n. So we will drop the subscript n. In the consequent manipulations will simply relate to it as r prime. To save some writing, and if we divide this relation by r prime n, which is r prime over here, we will arrive at the first relation, which is quite elegant. And this basically relation tells us that the distance from the line of centers to the center of the nth inverted circle divided by the radius of all these circles is precisely 2n. In addition to recovering the radius of the nth inscribed circle as a function of the radii of the input generating circles and its ordinal position, in my solution we will also recover the distance of the center of the nth inscribed circle. I refer to this distance as dn, to the straight line of centers that passes through the centers of the input generating circles. And we will also recover the shape of the distance from the tangency point T to the projection of the center of the nth inscribed circle onto the line of centers. This distance over here I describe as L sub n. And by doing so, we will implicitly introduce a certain coordinate system. The vertical or the y-axis of the system evidently will coincide with the line of centers. It will logically point up. This will be the y-axis, and the horizontal axis of this coordinate system will run at the bottom through the point T, let's say left to right. And by recovering the horizontal displacement dn and the vertical displacement ln of the center of the nth inscribed circle, we will know precisely the position of the center on of the nth inscribed circle in thus chosen coordinate system. And technically that also means that we will project the center of the nth inscribed circle, the point on, shown over here, onto the line of centers L in a traditional orthogonal fashion. In other words, the angle ON, DN, and T will be right. So the projection of the center of the nth inscribed circle ON onto the straight line of centers L, I will refer to as the point D sub n. D sub n, that's the point right here, and consequently the distance between the common tangency point T to the point dn will be the vertical displacement of the center of the nth inscribed circle, and thus our computation will be complete. And to that end, as I said before, a proper choice of inversion of the parent plane will transform this problem from very difficult to solve. If you try to solve this problem on your own without looking at the solution generated by Pappus and without using inversion, in all likelihood you will fail. It is a very difficult problem. Even though it is elementary, it is difficult, which means that if something is elementary, it doesn't mean it's easy. This problem is quite difficult, but with the proper choice of inversion, this problem, like I said, becomes accessible to any sufficiently motivated middle school student, because here all we have to do is construct a small number of right triangles, and after that the game is over. So what are these right triangles? Well, the first right triangle will be the triangle TDNON. That's the first right triangle. The similitude triangle of interest to us will be TO'0, and then O'N. It is this triangle right here, 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 and here. Also, again, because my drawing is by hand, it's a little bit silly, but let us pretend that the centers of our circles, the inscribed circle ON and the center of the nth inverted circle O'N, they must lie on one and the same straight line. That much we know from the machinery of inversive geometry. And we also know that inversion with respect to a circle conserves or preserves the points of tangency, or the magnitudes of angles, if you will, and that means that the straight line that passes through the center of inversion, that is important, through the center of inversion, and that is tangent to the nth inscribed circle at the point T sub n, will also be tangent to the image of that nth circle under the chosen inversion over here at the point T prime n. So this is another pair of right triangles, T, TN, ON, and T, T prime, N, O prime, N. Once we have these basically two pairs of right triangles figured out and locked in, game over. After that, what follows is an elementary, typical middle school computation. Nothing is quite difficult. And here we start with the observation that, as I mentioned before, the triangle TDNON, this is this triangle right here, the smaller triangle TDNON, this triangle, and the triangle TO'0, O'N, the triangle TO'0, O'N are similar by angle, angle, angle. That much is evident. The angles at the vertices DN and O'N are right by construction. This angle over here is evidently right too. The angle at the interior angle at the vertex T is shared by both of these triangles, TO'0, O'N. This angle right here is shared. The remaining angles must be the same. As such, by angle, 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 the triangles are similar, and by, let's say, Euclid's Elements Book 6, Proposition 4, if I'm not mistaken, the length of the corresponding sides about equal angles are in the same proportion. So based on the similarity of these two triangles, we construct our first proportion. dn, this distance dn, relates to this distance to the hypotenuse, to the length of the hypotenuse of the first triangle, TON, is the same as the ratio of the side d prime n. This is this distance right here. Remember, we computed that distance just a few seconds ago, as the distance relates to the length of the hypotenuse of the larger triangle. The distance from the point T to the point O'N, it is this distance right here. And again, if we move this distance into the numerator on the other side and this distance into the denominator, this is the relation that we obtain, and we can take it further at this point. Switching to the right triangles T, ON, TN, and T, O prime N, T prime N, we see that these right by construction triangles are similar again by angle, 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 because these triangles share the magnitude of the interior angle at T, at the vertex T right here. That magnitude is one and the same. The magnitude of the angles at the points Tn and T prime N is right by construction. It means that the magnitudes of the remaining angles must be the same, so these triangles are similar by AAA. And here again, just to make sure that we're all on the same page, the distance from the point ON to the point TN represents precisely the radius of the nth inscribed circle. This distance right here is designated with an arrow, and the distance between the points O prime n and T prime, and this distance represents the radius of the nth inverted circle R prime. Remember, we dropped the designation of its subscript n because the radii of all these inverted circles is one and the same. And again, we go back to the same Euclid's Elements book 6 proposition 4. The length of the sides in similar triangles that subtend the same angles are in the same proportion, where the corresponding sides lie opposite equal angles. And that means that in this case we can construct which proportion? Well, for the first triangle, we will construct the proportion between the hypotenuse again of that triangle. TON relates to the length of the radius Rn, this side. Rn TON to Rn, as this is in the same proportion as the length of the hypotenuse of the larger triangle TO prime n, as it relates to the length of the side O prime n Tn, which is basically the radius R prime of the radius of the inverted circles. And from that relation, from this proportion, we basically, this time, let's say we move the numerator of the right hand side into the denominator of the left hand side, and conversely the denominator of the left hand side into the numerator of the right hand side, and we obtain this proportion. And in the previous segment we just proved that the ratio of the same sides is shown on the left, and now we can do the following manipulation with this result. Since we just proved that the ratio of the distance dn to the distance d prime n is the same as the ratio of the radius of the nth inscribed circle to the radius of the nth inverted circle of that inscribed circle, it follows that if we swap the denominator on the left hand side with the numerator on the right hand side, if this ratio like so, we see that the ratio of the distance dn to the radius Rn of the nth inscribed circle is the same as the ratio between the distance d prime, and remember this is our distance from the point O prime and the center of the nth inverted circle to the line of centers L, to the radius of the nth inverted circle is 2n from the relationship number 1. Then we have it that this relationship shown on the left hand side is equal to 2n. Multiplying this relationship through by one copy of Rn, we arrive at our first useful relation shown over here. And this is actually quite amazing if you think about it on its own right. I will not go deep into any details, but we will refer to this relation as number 2. On your own, think about the fact that quite a lot of magnitudes that are connected to a circle are not only irrational but transcendental. We have two beautiful numbers, pi and e, the Euler's constant, if you will, that are connected to the circle. Both of these numbers are not only irrational, they're transcendental. But despite the fact that this bewilderingly complex relationship between the inscribed circles and the bounding generating circles is what it is nothing short of amazing that the distance of the center of the nth circle to the line of centers relates to the radius of that nth inscribed circle as an integral quantity. Look at this, 2n multiplied by the radius gives us the distance of the center of the nth circle to the line of centers. Spinning the similarity of the right triangles T, dn, on, and T, O prime 0, O prime n, One more time visually, this is these triangles T, DN, ON, and T, O prime 0, O prime N, these right triangles here and this guy right here. In the modern tongue, using the equality of the values of the corresponding trigonometric functions of tangent, we will say that the ratio of the distance ln to dn, distance ln to dn, which defines the trigonometric function of tangent of this angle, is the same as the corresponding distance t o prime 0. This is this distance right here. Maybe visually it will help you if I say it, if I will show this distance right here, this distance to this distance right here, o prime 0, o prime n, o prime 0, o prime n. This proportion must hold, but this distance we already know that we refer to it as d prime n. We deduce the relation for this distance as 2 times n times r prime. So from this relation over here, it follows that for the vertical displacement of the projection of the center ON of the nth inscribed circle onto the straight line of centers, this distance t dn, this is distance ln, we have dn. From this ratio, dn goes into the numerator, 2n in the denominator. This is in some sense one relation times the distance t o prime 0 divided by r prime, distance t o prime 0 divided by the distance or by the radius of the actually any inverted circle. We will refer to this relation as the relation number 3. Let us now express the distance between the point of tangency t and the point O prime 0 in terms of the given material, and we can do that as follows. Note that this distance can be represented as a compound quantity, as the diameter of the outer generating circle, the distance t a0. So here we write that the distance between the points t and O prime 0 is twice the radius r1, the radius of the outer generating circle, plus the distance, which is equal to half the distance between the points a0 and b prime 0. This is reflected over here, the distance between the points a0, b prime 0 over 2. And here we represent again the distance between the points a0, b prime 2 as a compound quantity, as the difference between the point t and the point b prime 0 minus precisely the diameter of the outer generating circle, the distance between the points t b prime 0 and twice the radius of the larger or outer generating circle. Now what do we have? We have 2r1 minus 1r1. That's one copy of r1, the radius of the outer generating circle, plus the ratio of t b prime 0, the distance between these 2 points, over 2. This is our relation that we will need in the future. I marked it as formula number 4. This 4 relates to over here. And now so far we haven't used in our symbolic shuffling the analytic representation of inversive geometry. Now is to do just that. Remember that the points b0 and b prime 0 are the inversive images of each other with respect to this circle of inversion that we define to have the center at the point t and having the radius of the diameter of the outer generating circle. Consequently, the product of the distances from the center of inversion to the point b0 and from the center of inversion to its image b prime 0 is the square of the radius of inversion. The radius of inversion is 2r1. The square of 2r1 is 4r squared 1. And we remember that the distance from the point of tangency to the point B0. That is how we constructed this point. Is the diameter of the inner generating circle is this distance right here. This is twice the radius R2, the radius of the inner generating circle, or its diameter. When we put 2R2 and 4R1 into our relation, 2 on the left side and 1 copy of 2 on the right side cancel each other out. And boom, voila, we have our relationship for the distance from the point T, point of tangency of the generating circles, to the point B prime O, to this point right here. That distance is given as 2 squares of the radius R1 over 1 copy of the radius R2. This will be relation number 5, this formula right here, number 5, this equal sign. And once we have the distance T B0 prime 0, we put it in this relationship in 4 over here, and this is a straightforward manipulation. The distance between the point of tangency of the generating circles T and the point O prime 0 is given as the ratio of the radii of the generating circles R1 divided by R2 multiplied by their sum. We now do essentially the same thing to the radius of the nth, or any for that matter, inverted circle, which is the distance from the point O prime 0 to either the point B prime 0 or A0, or in other words, half the distance from the point A0 to the point B prime 0. We capture this fact symbolically over here. The length of the radius of all the inverted circles, to which we refer as R prime, is equal to half the distance between the points A0 and B prime 0. Again, we represent that distance as a compound quantity, as the difference between the distances from the point T to the point B prime O and the diameter of the outer generating circle Q1. In other words, let's see if I can make it more visual for you. It will be this distance right here from the point T to the point B prime O minus the diameter of the outer generating circle. That circle is Q1, the inner generating circle Q2, but geometrically we have this distance right here, and we obtain our magnitude of the radius R prime, and we essentially go through the same exercise as we did before, except this time we use the relation number 5. That is why I ask you to number this relation. So from here, from this distance, we use the relation number 5 for the distance from the point T to the point B prime O. That distance was twice the square of the radius of the first circle divided by the radius of the second circle. We have 2 over here from this relation. We subtract 2R1 divided by 2, subtract R1. So this is a very straightforward manipulation. 2 and 2 cancel each other out on the left summand. So we have R square 1 minus, bringing the whole ratio back again to the same denominator. Let's say R1 times R2 divided by R2. Here R1, 1 copy of R1 can be factored out from both of the summands. Here there will be nothing left. Here there will be 1 copy of the radius R1. Thus we will form the ratio of the radii of the generating circles, and for the radius of each inverted circle R prime, we have the following relation: R1 divided by R2 times the difference. This time compare this formula to the previous formula that we obtained for the sum. This time there is a difference between the radii of the generating circles. We will number this relationship as number 7, and do realize that algebraically just about anything can make sense, but here the difference is a valid construct, and it always makes a geometric sense, because remember, in our case we picked or named our circles in such a way that we have the following constraint: R1 is greater than R2. 2. So when it comes to distances, this is a real and always strictly positive number. So this will be our relation number 7. Now take the relation number 7 and put it into the relation number 3. Recall that in the relation number 3 we discovered that the distance ln is the ratio of dn to 2n, which amazingly enough is basically rn, the radius of the nth inscribed circle. That was an amazing relationship that we established a few minutes ago, and then that relationship was multiplied by the distance from the point t to the point o prime 0 and divided by the radius r prime of the any circle that picked from the family of inverted circles. So for this distance, we remember we had the r1 divided by r2 times the sum of the radii r1 plus r2, and for the radius r prime we have r1 divided by r2 multiplied by the difference. So this is all we do over here. Ln is equal to, this ratio is rn times r1 divided by r2 times this sum, this is this distance, divided by what? R2 divided by r1, this is the inverse of this r1, and divided r prime, divided by the difference r1 minus r2. R1 and r1 here cancel out, r2 and r2 here cancel out, and voila, we have our relationship for the length Ln in terms of basically all the input material expressed as a function of Rn. And if you remember, obviously here I also have this relationship. We have dn equals 2n times Rn. So we have our two displacements, the horizontal displacement of the center of the nth inscribed circle and its vertical displacement with respect to the point t, d and l, and this relationship is equal to the radius of the nth inscribed circle times the ratio of the sum to the difference of the radii of the generating circles, r1 and r2. We will refer to this relation as the relation number 8. And now that we have expressed the distances dn and ln as a function of the length of the radius of the nth inscribed circle and the given local material, the length of the radii of the generating circles, q1 and q2, for a short home stretch, we can complete the solution of the problem and express the radius of the nth inscribed circle as a function of the lengths of the radius r1, r2, and the ordinal position of that circle n. And we do that by observing again that our triangles T, O, and Tn, and To prime and T prime n, which I described earlier. This is the triangle T, O, and Tn. This is the small triangle right here, and the larger triangle T, O prime and T prime n. Here is the tangent to both circles, the original circle, the inverted circle, the straight line that passes through the center of the original circle and that passes through the center of the inverted circle. Shared angle, angle is right, AAA, you know the story. Euclid's Elements, Book 6, Proposition 6, the length of the sides about the same angles in similar triangles where the sides lie opposite equal angles are in the same proportion. So we construct the following proportion: Rn, so this distance right here, Rn divided by the distance Ttn, the side, basically the ratio of the sides of a one right triangle, Rn to Ttn is the same as R prime, this distance right here, as it relates to the distance of that long side right here, Ttn. They're in the same proportion. From here we express Rn. Rn is R prime times the ratio Tn to Tt prime, and this is important right here. Now we go back again to the fact that we have what? We have a beautiful inversion of the parent plane with respect to a circle going on. So the tangency point Tn is taken into its image T prime n, and conversely T prime n is taken into Tn. What's important is that to that pair of points, when we can apply the analytic representation or analytic symbolization, if you will, of inversion. So the product of these two distances is equal to the square of the radius of inversion. The radius of inversion is twice the radius of the outer generating circle, 2r1 squared 4r2 4r1 squared. And from this relation over here, it follows that for the distance between the points T and Tn, for this distance right here, for this distance Tn, T, we have the following relationship: 4r squared 1 divided by the distance from the point T to the point Tn, this distance right here. Once we slug this relation back into here, it is important to realize that we have Rn is equal to R prime times 4r squared 1 divided by, look at this, I even put the power of the distance t prime n in red in order to underscore the fact that magically enough what pops out here is the square, not just the distance, but the square of the distance from the point T, the common point of tangency of the generating circles, to the image point, tangency point T prime. So this is a square. Now, we know R prime, the expression for R prime through relationship in 7 as the function of the length of the radii of the generating circles. That radius R prime is R1 divided by R2 times the difference, R1 minus R2, and the whole thing is multiplied again by 4r squared 1 divided by the square of the distance from the point T to the point T prime n. See, this is the square, this is important, and we know about the notion, the new notion that we learned in this course. This is the notion of the power of a point with respect to a circle. And in this case, look at this. The point T plays the role of what? Well, this is the point that is external with respect to the inverted nth circle shown over here. Consequently, the square of that distance represents what? Well, in our last lecture, we learned that the square of this distance represents precisely the power of the point T with respect to the nth inverted circle. And that precisely means that for the distance from the point T to the point T prime n squared, we have the following expression. This is the square of the distance from the point T to the point O prime n minus square of the radius of the corresponding circle, because remember again, the point T is taken outside of the circle K prime, let's say, kth inverted circle, and that square of this distance right here shown on the left side of your screen is the power of the point T with respect to that circle, or in some sense, if you will, this is the side effect of the Pythagorean theorem. So this expression over here stands alone. Do not mix it up with anything else. This expression terminates over here. This is this guy. So now the only thing, we already know the expression for the radius r prime in terms of the local material. So now our ability to compute the requested magnitude, the radius of the nth inscribed circle over here shown in blue in terms of the local material, on our ability to compute the square of this distance. But this is trivial. We take the square of this distance from the triangle TO prime 0 O prime, and is this triangle right here, because all the material in that triangle already available to us in its through its local material. For the square of this distance right here, we have TO prime 0 squared, it is this distance, plus the square of the distance d prime n, we already know what it is. it is for n r prime squared. And we can take this distance from the relation number 6. Don't forget that we numbered our relations carefully, and hopefully your numbering coincides with mine. So from the relation number 6 for this distance, once we put it in and accommodate this term right here, we will have the expression shown over here. Again, I apologize, my space is tight over here on the board, but this is the expression that we're looking for. Concentrate on this piece right here. This equal sign is carried into this equal sign. I bumped it up so I have room for the expression at the bottom, but again, square of the ratio times the square of the sum plus 4n squared times, again, square of the ratio times the square of the difference. And essentially this is it. The computational part is over. We now take this result and put it over here. And remember that we also have minus r prime squared. And once we unwind all the material that we have over here in terms of local variables, r1, r2, and n, we will obtain the expression shown over here. The distance from the point t to the point t prime n squared, the square of the distance, is represented by the square of the ratio of the radii r1 and r2 multiplied by, remember, this parenthesis right here terminates with this parenthesis, is balanced with this parenthesis. So inside we have the sum of the radii r1 and r2 squared plus 4n squared minus 1 times the square of the difference of the radii r1 and r2. And once we have the square of this distance, we will simply plug it in over here. I took the liberty to rearrange the relations that we developed in the previous segment, but do you understand what it is? Number 9 pertains to this relation, and number 10 pertains to this. So we now take the square of this distance and slug it into this relation over here. In the relation number 10, everything is known. R prime in terms of the local material is known, 4 is a constant, r squared 1 is known, and this expression is taken from over here, and this is the result. And once we carefully align all the given material that is known to us, the radii of the generating circles r1 and r2 and the ordinal number of the nth inscribed circle, then we will have the following expression for the radius, or for the length of the radius of the nth inscribed circle. It will be a function that is rational in this radii and the ordinal number of that circle, and in the numerator we'll have the following product: 4 times r1 times r2 times the difference between the length of the radii r1 and r2. And that difference, remember, always makes geometric sense because we have r1 strictly greater than r2. And in the denominator we'll have the sum of the following two terms: r1 plus r2 squared plus 4n squared minus 1 multiplied by the square of the difference of the radii r1 minus r2. And once we unwind the expressions for the horizontal displacement, dn of the center of the nth inscribed circle in terms of the locally available material, remember, dn is 2n times rn, so we multiply this number by 2n. 4 becomes 8. Another factor of n pops into the numerator of the expression for Rn. Denominator is the same. The denominator here and the denominator here is the same. And we have a similar expression for the vertical displacement of the projection of the center of the nth inscribed circle onto the line of centers. Ln is equal to, here I wrote this expression in green so that you can see that here we have the sum of the radii r1 plus r2 difference, but here is a sum for r1 times r2 divided by the same denominator. Remember that for ln we had which expression? This rn the radius of the nth inscribed circle times what? In the numerator, we had the sum. In the denominator, we had the difference of the radii. Difference and difference cancel out, and the sum survives and percolates into the numerator. Game over, problem solved. Again, this is really an amazing problem. Without the machinery of inversive geometry, this problem is really not trivial at all. The computations are quite heavy and are not easy on the eye. With the corresponding and cleverly chosen inversion centered at the point T with the radius that is equal to twice the radius of the larger generating circle, the problem becomes a walk in the park. Any sufficiently motivated middle school student should be able to solve this problem inside of, let's say, 30 minutes, because all it is a play on two pairs of very evident right triangles, and this is it. If you have any questions, then the comment section is open. Ask away. Before you ask your question, try to dig through the printed material. The link to the chapter on which this seminar is based is in the comment section. Be my guest. Read through that printed material first. Then again, if something is not clear, by all means do ask the question. In the next seminar, that will be our officially last seminar of this course. After that, we'll begin our practice sessions. We will solve another very interesting and in some sense amazing problem. This problem will be called the Arbelos encounter. We will need the formation where half the circle is partitioned into a curvilinear, let's say, triangle, if you will, this area right here, where the straight line perpendicular to the point where two smaller circles meet is constructed, and into the space right here, two circles are inscribed. Amazingly enough, regardless of where this point rests on the diameter of the generating semicircle, the length of the radii of these two circles, again, amazingly enough, will be the same, and this is what we will have to prove in the next seminar.